There is a kind of work that can only be done at night, and only by someone who knows what to look for. A freight train is moving through open country in the middle of the 20th century. It is long, it is heavy, and it is being watched. Somewhere along the line stands a railroad man with a lantern, and he is not looking at the locomotive, or the cars, or the couplers. He is looking at a row of small steel boxes riding just above the wheels, and he is looking for one thing only: a glow, a thread of smoke, a smell that does not belong. Inside each of those boxes is a block of brass, resting on a polished section of the axle. Underneath, packed into the bottom of the box, is a mass of cotton or wool waste, soaked in oil. As the axle turns, it drags a film of that oil up between itself and the brass, and the whole weight of the car, the steel, the timber, the grain, the coal, rides on that film. The film is thinner than a sheet of paper. It is thinner than a human hair, and it is the only thing standing between the axle and the brass. If the oil leaks away, or dries out, or if a single strand of that packing works its way up into the gap and interrupts the flow, the film breaks. Steel touches brass. The temperature does not climb slowly. It climbs the way a brake climbs on a long grade. And within minutes, the oil-soaked waste is not a lubricant anymore. It is fuel. Railroaders had a name for it. They called it a hot box. The remarkable thing is not that it happened. The remarkable thing is what it reveals. An industry that could build locomotives weighing hundreds of tons, that could bridge rivers and tunnel through mountains, still depended, at the very last inch, on whether a small quantity of oil had found its way into a gap the width of a fingerprint. That gap is what tonight is about. You are almost certainly within a few feet of one right now. If there is a refrigerator in the room, there is a compressor inside it, and inside that compressor there is a crankshaft turning in oil. If there is a ceiling fan, there is a shaft riding in a bearing that was packed with grease at the factory and has not been touched since. A washing machine, a furnace blower, a cordless drill, a car in the driveway with a crankshaft spinning at a few thousand revolutions per minute, supported by nothing but pressurized oil. None of these things are exotic. They are the ordinary furniture of modern life, and every one of them is running on a film of liquid that nobody can see, that nobody thinks about, and that has to be there continuously, without interruption, for years. In our last episode, we followed the long effort to replace sliding friction with rolling motion, the centuries of work that produced the ball bearing, and the harder, stranger work of learning to manufacture a steel sphere accurate enough to be useful. It was a genuine solution. Rolling is cheaper than sliding in every sense that matters to an engineer. But it is worth being precise about what the ball bearing actually accomplished, because it is easy to overstate it. Rolling motion did not eliminate contact between metal parts. It concentrated that contact into a very small area and moved it constantly. The ball still touches the raceway. It touches it at a spot smaller than the head of a pin, and it touches it under enormous pressure, and it does so several thousand times a minute. Run a bearing like that dry, a good one, a precise one, made of properly hardened steel, and it will destroy itself. Not over years, over minutes. To understand why, it helps to abandon a picture most of us carry around without noticing. We think of a polished metal surface as smooth. It looks smooth. It feels smooth. Draw your thumb across a ground shaft or a machined face, and there is nothing to catch on. but that impression comes from a hand that cannot resolve anything smaller than a few thousandths of an inch, and the surface is not built at that scale. Put that same surface under sufficient magnification, and the flatness disappears. What replaces it is terrain, ridges, peaks, shallow valleys, the frozen record of whatever tool last passed over it. Engineers call the peaks asperities. Even on a finely ground surface, they are there. Now press two such surfaces together. They do not meet across their whole apparent area. They meet at the tips of the tallest peaks, and only there. The real area of contact, the area actually carrying the load, turns out to be a small fraction of the area you can see. This was established experimentally in the middle of the 20th century by Frank Philip Bowden and David Tabor, working in Cambridge, and it reframed the entire subject. If two surfaces only touch at a scattering of high points, then the load is not spread out at all. It is concentrated on those points, and the pressure at each of them can be high enough to make the metal yield. What happens next is the part that surprises people. Under that pressure, and with clean metal on both sides, the two surfaces can weld, not with heat from a torch, with pressure and intimacy. The atoms of one peak get close enough to the atoms of the other that they stop being two separate pieces of steel. Then the shaft keeps turning, and those tiny welds have to break. They break in the weaker of the two metals, tearing material out and dragging it along. That torn material becomes debris. The debris scores the surface, which creates more high points, which creates more contact, which creates more heat. That is adhesive wear, and it is not a slow decline, it is a runaway. So the problem was never really friction in the way the word is usually meant. Friction is a symptom. The problem is contact, and the whole history we are about to follow is the history of one stubborn, unglamorous ambition. Keep them apart. The evidence is thin, and it is thin for an honest reason. Almost every substance ancient people would have used to reduce friction was organic. Animal fat, vegetable oil, beeswax, tallow rendered from sheep or cattle. These things do not survive 4,000 years in the ground. They oxidize, they are eaten, they wash away. What survives is the hardware, a wheel, an axle, a hub, and occasionally a residue, and occasionally a picture. One of those pictures is famous enough that it has found its way into engineering textbooks. It comes from a tomb at Deir el-Bersha in Middle Egypt, and it dates to roughly 1880 BC. The tomb belonged to a man named Jehuti-Hotep, who was not a pharaoh, but a nomarch, a provincial governor of the Middle Kingdom. The painted scene shows a colossal seated statue of him being moved on a wooden sledge. Ropes run forward from the sledge to long files of men, and standing on the front of the sledge itself, there is a single figure pouring liquid from a vessel onto the ground directly ahead of the runners. For a long time this was read as a religious act, a libation, a ritual offering poured before an image of an important man. That reading is not unreasonable. Egyptian art is full of ritual. In 2014, a group of physicists working in Amsterdam approached it from the other direction. They built a laboratory version, a small sledge, a tray of sand, and a way to measure the force required to pull it. Then they varied how wet the sand was. Dry sand behaved badly. As the sledge advanced, it pushed up a heap of loose grains in front of itself, and that heap had to be shoved along, adding steadily to the required force. But adding a modest amount of water change the behavior of the sand itself. Water forms tiny bridges between grains, holding them to one another, the same effect that lets you build a sandcastle out of damp sand and not out of dry. The stiffened sand stopped piling up. In their experiments, getting the water content into the right range cut the pulling force by roughly half, depending on the type of sand. Too little water, and the effect vanished. Too much, and it vanished again. There was an optimum, and the optimum was narrow. Now, it is worth saying clearly what this does and does not show. Egyptologists have generally been more cautious about the scene than engineers have, and their caution is fair. A painting is not a laboratory notebook. It does not tell us whether the practice was understood as a technique or performed as a rite, or both at once, which is probably the likeliest answer of all, and there is a technical distinction worth keeping. What the wet sand does is not what oil does in a bearing. There is no fluid film separating two surfaces here. The sand is being made rigid, not slippery. It belongs to a different branch of the same subject. But the deeper point survives the caution. Whatever they believed they were doing, somebody in Middle Kingdom Egypt had worked out. By watching, by repetition, by the accumulated judgment of men who moved heavy objects for a living, that the ground in front of a loaded sledge should be treated before the sledge arrived. Where we can be more confident is the wheel. 6 chariots were found in the tomb of Tutankhamun, and they have been studied closely since Howard Carter's excavation in the 1920s. They are extraordinarily light, the whole vehicle built from bent and glued wood, rawhide binding and leather. The wheel turns on a wooden axle, running inside a long wooden hub, and there is a leather lining at the interface. A study published in 2000 examined the mechanics of these chariots in detail and described the arrangement, the spokes, the sleeve-bearing materials, the use of animal fat for lubrication, as comparable in quality to European carts of the 19th century AD. The animal fat is the part that concerns us. Wood turning inside wood at speed, carrying the weight of a vehicle and its riders, generates heat, and wood is an excellent insulator, which means the heat has nowhere to go. Grease between the two is not a refinement. It is the difference between a working chariot and a smoking one. Elsewhere in the ancient world, the same problem produced the same answers. Bitumen, natural asphalt, seeping from the ground around the Dead Sea and in Mesopotamia, was used as a sealant and a heavy lubricant. In the Mediterranean world, olive oil was abundant and did the light work. Tallow did the heavy work, because tallow stays where you put it. That last property is worth pausing on, because it will come back. A liquid oil runs out of an open bearing. A stiff fat does not. Everything we will later call grease is a variation on that single insight, and for a very long time this was enough. It was enough because almost nothing turned fast. A cartwheel, a potter's wheel, a mill shaft driven by water or by animals, these are slow machines, lightly loaded by later standards, and slow machines forgive a great deal. The moment that stopped being true, the entire subject had to be reinvented. Between roughly 1493 and the end of his life, Leonardo da Vinci filled notebook pages with sliding blocks. They are unassuming sketches, a block on a flat surface with a cord running over a pulley to a hanging weight, a block on an inclined plane. The same block turned onto a different face. He drew these arrangements repeatedly across more than 20 years, and alongside them he wrote down what he had found. He found 2 things. The first is that the force needed to drag an object depends on how heavily it presses down. Double the weight, he wrote in effect, and you double the effort. The relationship is proportional. The second is far less obvious, and to this day, people find it counterintuitive when they first hear it. He found that the force does not depend on how much surface is in contact. Stand the same block on its narrow edge instead of its broad face, and the effort required to slide it does not change. Those two statements are the classical laws of friction. Leonardo had them at the end of the 15th century, and they went nowhere because he never published. The notebooks were dispersed after his death, some caches not recovered until the 20th century, and one of the key pages, studied by Ian Hutchings at Cambridge and published in 2016, had been overlooked for generations, partly because scholars looking at it were drawn to a sketch of an old woman's head in the same margin. So the laws had to be found again. They were, in 1699, by the French physicist Guillaume Amontons, who presented them to the Royal Academy of Sciences in Paris, and who appears to have known nothing of Leonardo's work. They carry his name today. Amontons added something Leonardo had not emphasized, that when surfaces were well lubricated, the friction became remarkably insensitive to what the surfaces were actually made of. Grease between them mattered more than whether they were iron or brass. Half a century later, Leonhard Euler took up the problem and drew a distinction that anybody who has ever pushed a heavy crate already knows in their body, that it takes more force to get something moving than to keep it moving. Static friction and kinetic friction became separate quantities. Then, in the 1780s, Charles Augustin de Coulomb, a military engineer with a practical interest in ropes, machines, and the fortification works of the French army, ran the experiments again, with more care than anyone before him. Coulomb confirmed the earlier laws, examined how friction changed with speed, and measured how the force needed to start a motion grew if two surfaces had been left resting against each other for a while. By the end of the 18th century, then, friction had become a number. You could put a coefficient in a calculation. You could design against it. What nobody could do was explain what a lubricant was for. Everyone knew oil worked. Every millwright and wheelwright and clockmaker in Europe knew it worked. The prevailing picture, insofar as there was one, was that oil somehow smoothed things, filled in the roughness, coated the peaks, let them glide. It was a picture of oil as a very thin, very slippery layer stuck to the metal. That picture is not entirely wrong. It describes one real regime of lubrication, and we will come back to it under its proper name. But as an explanation of what happens inside a loaded, fast-turning bearing, it is badly incomplete, and the incompleteness would not be discovered for another 100 years. In the meantime, the machines were about to get much, much faster. Walk into a textile mill in Lancashire or Massachusetts in the 1840s, and the first thing that reaches you is the noise, and the second is the smell. The noise comes from the transmission system. Power arrives from a water wheel or a steam engine at one end of the building and has to be distributed to every machine in it. The solution of the period was line shafting, long steel shafts running the length of the ceiling, turning continuously, carrying pulleys, with leather belts dropping down from those pulleys to each individual loom or spindle or lathe. A single mill might contain hundreds of feet of shafting. Every 20 feet or so, that shaft rests in a bearing, usually a split cast iron housing with a bronze or babbitt liner, bolted to a beam. Hundreds of bearings. all of them turning all day, all of them needing oil. The smell is that oil, warm. The job of supplying it belonged to a person. In many mills that person was a boy, because the work was repetitive and the wage was low, and because a boy could get up into the framing where a grown man could not comfortably go. He carried a long-spouted can, and he went around the building on a circuit, and when he had finished the circuit, he started it again. He did this while the shafting was turning. There was no other option. Stopping the mill meant stopping production. Reaching an oil hole meant reaching past a moving belt, and the accident records of the period are not pleasant reading. There were mechanical aids. The simplest was a cup mounted over the bearing with a wick of cotton or worsted hanging down through a hole. Capillary action drew oil up the wick and let it drip onto the shaft, slowly, steadily, and without anyone having to be there. Better versions added a needle valve or a lift arrangement so the feed could be shut off when the machine stopped. These were real improvements. They were also, from an engineering standpoint, unsatisfying, and it is worth being precise about why. A wick feed does not know anything. It does not know how fast the shaft is turning, or how hot the bearing is, or how heavily it is loaded. It delivers roughly the same amount of oil whether the machine is straining or idling. Set it too lean and you get a hot bearing. Set it too rich and you get oil on the floor, oil on the product, and a bill at the end of the month. And then there was the oil itself, which had a problem no adjustment could fix. The lubricants of the period were animal and vegetable in origin. Tallow, lard oil, neat's foot oil rendered from cattle bones and feet, olive oil and rapeseed oil, which the British called colza, castor oil for the heaviest duties. These are fine lubricants in many respects. They cling to metal well, better in fact than the mineral oils that would replace them. But they are chemically alive. Exposed to air and warmth, animal and vegetable oils oxidize. They go rancid. They turn acidic and begin to attack the bearing metal they were supposed to protect. They thicken into gum, and the gum blocks the very oil holes and wick feeds that were meant to deliver more oil. A bearing that had been running sweetly for a season could be strangled by the residue of its own lubricant. Millwrights knew all this. They dealt with it by cleaning constantly, flushing passages, replacing oil on a schedule, and accepting a certain rate of trouble as the cost of doing business. What they could not do was make the machines slower. Through the middle decades of the 19th century, spindle speeds went up, engine speeds went up, and the temperature inside the bearings went up with them. The old oils were being asked to work in conditions their chemistry could not survive. The industry needed something better, and it found something better in a very unlikely place. In the harbor at New Bedford, Massachusetts, in the 1840s, you could stand on the wharf and watch barrels come ashore from ships that had been at sea for 3 years. The sperm whale has, in the front of its enormous head, an organ filled with a pale liquid wax. Whalers called it the case, and the material inside it spermaceti. A single large animal might yield a great many barrels of it. Cut into the case, and the substance runs out clear and thin. Let it cool, and part of it sets into a soft white solid that made the finest candles in the world. The rest, the liquid fraction, called sperm oil, turned out to be one of the best lubricants human beings had ever laid hands on, and for a reason that is chemically specific. Almost all the animal and vegetable oils of the period are triglycerides. Sperm oil is not. It is composed largely of wax esters, which are a different molecular arrangement, and that difference gives it a different personality. It resisted oxidation better than the tallows and seed oils. It stayed fluid at low temperatures. It clung to metal. It performed well in very thin films, under light loads and high speeds, which is exactly the condition inside a delicate mechanism. That last property made it indispensable in places most people never thought about. Clocks and watches ran on sperm oil. Chronometers, on which navigation depended, ran on sperm oil. Sewing machines, textile spindles, precision instruments, gun mechanisms. If a device was small and had to keep working without attention for years, the oil in it very likely came out of the head of a whale. There is something genuinely strange about this, and it is worth sitting with for a moment. The Industrial Revolution is normally pictured as coal and iron, as furnaces and forges, and things dug out of the ground. But a considerable portion of the machinery of that revolution was kept alive by a hunt. Ships sailed from Nantucket and New Bedford into the Pacific and stayed there for years at a time, and the reason they went was that the machines back home needed to be lubricated, and there was no better way to do it. The economics were as strange as the chemistry. The supply of a critical industrial material depended on weather, on navigation, on where the whales happened to be that season, and on whether a ship came home at all. Prices swung wildly. Sperm oil was expensive in the best years and ruinous in the bad ones, and the resource was finite in a way the industry was slow to admit. Sperm whale populations in the accessible grounds were being drawn down. Voyages got longer because the near waters had been fished out. By the middle of the 19th century, the cost of whale oil was climbing steadily, and anybody with an interest in the subject could see the shape of the curve. So there was a market waiting, a large, impatient, well-funded market for any substance that could do what sperm oil did without requiring a 3-year voyage. The substance existed. It was in the ground in western Pennsylvania. It had been seeping into creeks there for as long as anyone could remember, and nobody had yet found a use for it that justified the trouble of collecting it. We should note, before we leave the whales, that this is not quite the end of their part in the story. Sperm oil was harder to replace than anyone expected, and it stayed in service in one particular application deep into the 20th century, long past the point where most people would guess. We will come back to that. Consider the problem facing a locomotive engineer in the 1850s, because it is a genuinely nasty one. Inside the cylinders of a steam locomotive, a piston is sliding back and forth against the cylinder wall. The steam around it is hot and under pressure. The piston is fitted with rings pressing outward against the bore. Metal is sliding on metal at speed, continuously, and it needs oil. The oil cannot be applied from outside, because the cylinder is a sealed pressure vessel. It cannot be applied by a man with a can, because the locomotive is moving at 40 miles an hour with a train behind it. It cannot be poured in beforehand and expected to last, because steam and exhaust carry it away. It has to be delivered continuously from a reservoir against boiler pressure into a hot chamber without anyone touching anything. The device that solved this is one of the most elegant small machines of the 19th century, and it has almost no moving parts at all. John Ramsbottom was locomotive superintendent for the London and North Western Railway, based eventually at the Crewe Works, and he was one of those figures who appears repeatedly in the mechanical history of the period. The split piston ring is his, the Ramsbottom safety valve is his, and in the second half of the 1850s, The sources differ on the exact date, with some placing his displacement lubricator around 1856 and others dating its introduction to 1860. He produced the arrangement that bears his name. Here is how it works, and it rewards attention. A closed brass vessel is filled with heavy oil and connected by a small pipe to the steam supply. Open a valve, and steam enters the top of the vessel. Inside, away from the fire, the steam cools and condenses back into water. Water is denser than oil, so it sinks. It collects at the bottom of the vessel and, drop by drop, it lifts the oil above it. The oil, having nowhere else to go, rises and spills out through the delivery pipe into the steam line, where the moving steam carries it into the cylinders as a fine mist. There is no pump, there is no linkage. The engine's own steam does the work, and it does it only while the engine is working. That last detail is both the beauty of the design and its central weakness. Coasting with the regulator closed, there is no steam entering the vessel, so there is no condensation, so there is no oil, at exactly the moment when the pistons are still sliding. And the feed rate was governed by how fast the steam condensed, which meant it was governed by the weather. On a cold day, the lubricator ran rich. On a warm day, it ran lean. Engine men learned to compensate by feel and by experience, which is another way of saying that the device did not really work by itself. James Roscoe addressed part of this in 1862, in a design covered by British Patent 11337. Roscoe added a control valve so the driver could regulate how much steam reached the lubricator, and an air-filled chamber inside the oil reservoir that helped maintain some delivery when steam was cut off. Setting the valve correctly still took judgment, and the right setting depended on how fast the train was running. But it was a real improvement, and Roscoe lubricators stayed in use on locomotives for a very long time. Across the Atlantic, a man was working on the same family of problems from a different direction, and his name has become attached to the whole subject in a way that deserves careful handling. Elijah McCoy was born in 1844 in Colchester, in what is now Ontario. His parents had been born into slavery in Kentucky and had escaped to Canada by way of the Underground Railroad. The family later moved back across the border and settled in Ypsilanti, Michigan. As a young man, McCoy went to Edinburgh to train in mechanical engineering, and when he returned to Michigan, he found that the work available to him, despite that training, was a job as a fireman and oiler on the Michigan Central Railroad, which is to say that he spent his working days doing exactly the labor we have been describing, shoveling coal and going around a locomotive with a can, putting oil where oil needed to go. He also kept a machine shop at home, and on July 23, 1872, he was granted United States Patent 129,843, titled Improvement in Lubricators for Steam Engines. Over the following 2 years, he took out further patents refining it, and across his life he accumulated dozens more. The usual figure given is 57, covering lubricating devices and a scattering of other inventions. His lubricators worked, and they spread. By 1899, the Michigan Bureau of Labor and Industrial Statistics reported his design in use on very nearly all the railroads of North America. Now, 2 corrections, because this story is usually told badly, and telling it accurately does not diminish McCoy in the slightest. The first is that McCoy did not invent the automatic lubricator. Displacement lubricators of the Ramsbottom and Roscoe type were already in widespread service on both sides of the Atlantic before his 1872 patent, and their descendants stayed in use well into the 20th century. McCoy entered a field that already existed and produced a version that was better made, better regarded, and more successful than most of its competitors. That is an achievement of a different kind, and a common one in engineering history, the difference between having an idea and having the version people actually want to buy. The second correction concerns a phrase. You will very often hear that buyers, wary of inferior copies, began asking for the real McCoy, and that this is the origin of the expression. It is a wonderful story. The evidence does not support it. The earliest recorded form of the phrase appears in 1856, before McCoy's patent, before he was old enough to have invented anything, in a Scottish poem referring to whiskey, a drop of the real Mackay. By 1870, an Edinburgh distilling firm had adopted the real Mackay as an advertising slogan, and the first known figurative use in the modern sense appears in a letter written by Robert Louis Stevenson in 1883. The early examples are all spelled Mackay or Mackay, and they all concern strong drink. How the Scottish spelling became the American one is not fully settled, though the fame of a boxer named Kid McCoy in the 1890s is the usual suspect. The connection to Elijah McCoy appears to have been attached to the phrase much later. It turns up in an advertisement in the 1960s, and to have stuck because it is a better story than a whiskey slogan. He does not need it. A man born to parents who escaped slavery, trained as an engineer, denied engineering work, who solved from the footplate a problem that the railroads of a continent were struggling with, and who kept refining it for 50 years, has a legacy that does not require a borrowed idiom. If you find these quiet journeys through the mechanical world worth returning to, subscribing is the simplest way to find the next part of the series when it arrives. Almost nobody who drilled for oil in the 1860s was looking for lubricant. When Edwin Drake's well came in near Titusville, Pennsylvania, in 1859, and when the rush that followed covered the creek valleys of western Pennsylvania with derricks, the product everyone wanted was kerosene, lamp oil, a cheap, bright, reliable illuminant to replace the whale oil that had been getting more expensive every year. That was where the money was, and that was what the refineries were built to make. Crude oil is not one substance. It is a mixture of hydrocarbon molecules of many different sizes, and the way you separate them is by boiling. Heat the crude, and the smallest, lightest molecules boil off first. Collect those separately, keep heating, and progressively heavier fractions come over. Kerosene sits comfortably in the middle of that range. What refiners did not want was what was left at the bottom of the still after the kerosene had gone. A dark, heavy, viscous residue made of the largest molecules, too thick to burn in a lamp, hard to handle, and produced in quantity whether you wanted it or not. It was a disposal problem, except that it was oily, very oily, and there were people who noticed. There is more than one claimant to what happened next, which is normal in this kind of history, and worth stating plainly rather than resolving artificially. In Rochester, New York, in 1866, a carpenter named Matthew Ewing and a man named Hiram Bond Everest were experimenting with a way of distilling crude under reduced pressure. Their goal was kerosene, and as a kerosene process, it was a failure. But Everest examined the oily residue it left behind and concluded that it had a future as a lubricant. They founded the Vacuum Oil Company on that judgment. Everest is said to have loaded a cart with cans of the stuff and gone around selling it, initially as a harness oil for leather, and the company's early advertising made an argument that any factory owner could follow. Friction costs more than lubrication. In the same year, in Binghamton, New York, a physician named John Ellis was working on a related idea and founded a refining business to produce lubricating oil from petroleum for steam engines. Over the next 2 years, he took out several patents on a high-viscosity, all-petroleum cylinder oil intended to hold up under heat. The brand name he eventually chose for it was Valvoline. Both firms describe themselves, in one formulation or another, as the origin of petroleum lubrication. Both were founded in 1866. It is more accurate and more interesting to say that the industry had a problem and a surplus at the same moment, and that several people connected them independently. The technical point underneath the corporate one is the vacuum distillation, and it is worth explaining because it is the reason petroleum lubricants became good rather than merely available. The heavy molecules that make a useful lubricant boil at very high temperatures. If you try to distill them at ordinary atmospheric pressure, you have to heat the residue so hot that the molecules begin to break apart before they evaporate. You get cracking, discoloration, and a product full of decomposition compounds that will form varnish and sludge in service. Lower the pressure above the liquid, however, and everything boils at a lower temperature. Pull a vacuum on the still, and you can bring those heavy fractions over as vapor while keeping the temperature low enough that the molecules survive the trip intact. Vacuum oil's process combined reduced pressure with injected superheated steam to push the effective temperature lower still. The result was a clean, pale, stable heavy oil that could be graded and sold. Vacuum's Gargoyle 600W steam cylinder oil became a mainstay of industrial lubrication, and the company was successful enough that Standard Oil bought a 3/4 interest in it in 1879 for $200,000. Its later trademark, Mobile, is still on the market. What this meant, practically, is that for the first time in human history, the supply of lubricant was decoupled from agriculture and from hunting. It no longer depended on the olive harvest or the tallow yield of a slaughterhouse or whether the whaling fleet had a good season. It came out of the ground in quantity. It was consistent from barrel to barrel, and it did not go rancid. Machines could now be oiled without limit. And this is precisely the moment to notice a gap that had opened up and that almost nobody was talking about. The world now had abundant, cheap, stable lubricating oil, an industry devoted to producing it, and grading systems being argued over in trade journals. Nobody could explain what it did, not vaguely, specifically. Ask the best engineer in Britain in 1880 how a film of oil supports the weight of a railway carriage, and you would get an answer about oil coating the surfaces and reducing their tendency to seize. That answer describes something real, but it does not explain the numbers, and within 3 years an experiment was going to make the gap impossible to ignore. The Institution of Mechanical Engineers had a practical reason to be interested in friction. Britain's railways were consuming a great deal of oil in their axle bearings. They were losing a measurable amount of power to friction in those bearings, and hot boxes cost money, and occasionally cost more than money. So the institution formed a research committee on friction at high velocities, and commissioned a series of experiments to determine in a systematic way the best method of lubricating a railway journal. The man they engaged was Beauchamp Tower. He was an engineer and an inventor who had worked as a research assistant to William Froude and to Lord Rayleigh, the latter also a personal friend and a member of the committee. He was, by all accounts, a careful and inventive experimentalist, which turned out to matter enormously. Tower built a rig that reproduced a railway journal bearing at working scale. A steel shaft, 4 inches in diameter, turning inside a partial bronze bearing, partial meaning it wrapped over the top of the shaft rather than enclosing it, exactly as a railway journal bearing does. The bearing surface was about 6 inches long. He could load it, drive it at various speeds, and measure the friction. His first results were interesting but not shocking. He tried several methods of getting oil to the bearing, and the method that gave the lowest friction by a wide margin was the simplest one available, sitting the shaft in a bath of oil so that it carried lubricant up with it as it turned. The measured friction with bath lubrication was remarkably low. Then he set out to try a different arrangement, feeding oil from above, from a siphon lubricator, the way a real journal box might be fed. To do this, he needed a hole in the top of the bronze bearing, so he drilled one 1/2 inch across, right in the middle of the loaded region. He filled the bearing with oil. He started the shaft, and the oil came up out of the hole, not a seep. It rose and overflowed. Tower did the sensible thing and plugged the hole with a wooden bung. The bung was pushed out. He fitted it again. Harder. It was pushed out again. At this point, Tower stopped treating the hole as an inconvenience and started treating it as an instrument. He fitted a pressure gauge to it. Then he drilled more holes at different positions around and along the bearing and gauged those too. What he found is one of the genuinely great results in the history of machinery. There was pressure in the oil film. Substantial pressure, hundreds of pounds per square inch. It was not uniform. It varied from point to point, low at the leading edge, rising to a peak somewhere inside the loaded arc, falling away again. He mapped it out. Then he did the arithmetic. He took his measured pressure distribution, integrated it over the area of the bearing, and compared the total to the load he had hung on the machine. They matched. The entire load on the bearing was being carried by pressure in the oil, not partly, not mostly. The oil film was supporting the shaft, and the bronze, the expensive, carefully fitted, carefully scraped bronze that everyone thought of as the bearing, was not touching the steel at all. It is worth pausing on how strange this would have seemed. The whole vocabulary of the trade assumed contact. You talked about bearing metal, about which alloy stood up best, about the surface finish of the journal, about bedding a bearing in so it would carry evenly. All of that language describes two solid bodies meeting each other, and Tower's gauges said that under the right conditions, they never met. He published 2 reports for the institution, the first on the friction of lubricated bearings in 1883, and a second in 1885, specifically on the oil pressure he had found. Tower himself did not produce a theory. He was scrupulous about that. He reported what his instruments told him. He had discovered the phenomenon and measured it accurately, and he left it there. But the reports were read, and among the people reading them was a professor at Owens College in Manchester who happened to be one of the finest fluid dynamicists alive. Osborne Reynolds encountered Tower's results shortly after the first report appeared, mentioned them at the British Association meeting in 1884, and then went after the problem with considerable energy. His paper, On the Theory of Lubrication and its Application to Mr. Beauchamp Tower's Experiments, appeared in the Philosophical Transactions of the Royal Society in 1886. The explanation he arrived at is one of those ideas that seems obvious the moment somebody says it and is invisible until they do. Start with a shaft sitting in a bearing that is very slightly larger than it is, and it must be slightly larger, or it could not turn at all. That clearance is not a defect, it is the whole mechanism. When the shaft is at rest under load, it settles to the bottom, and the gap between shaft and bearing is at its narrowest directly underneath and widest at the top. Now start the shaft turning. The oil immediately next to the shaft surface is dragged around with it. That is simply what a viscous liquid does against a moving wall. So the shaft is continuously carrying oil around into the narrowing part of the gap. And here is the crux. Liquid is essentially incompressible. You cannot squeeze it into a smaller volume. If a moving surface is dragging liquid into a space that gets progressively narrower, and the liquid cannot compress and cannot instantly escape sideways, then the pressure in that converging region must rise. It rises high enough to lift the shaft. Reynolds worked out that the shaft's center does not sit directly below the bearing's center once it is running. It shifts sideways so that the oil film is thicker on the incoming side and thinner on the outgoing side, forming a converging wedge of liquid, and the position it settles into is precisely the position where the pressure generated in that wedge balances the applied load. There is a rough, everyday analogy. Drag your finger across a wet countertop with a little pressure, and you can feel a moment where the water builds ahead of your fingertip and briefly holds it up. That is the same effect. Motion, a converging gap, a liquid that will not compress. The analogy fails in two ways worth naming. Your finger is soft and the countertop is rough, and the speeds involved are trivial. In a real bearing, the pressures are hundreds or thousands of times higher, and the film is measured in 10,000ths of an inch. But the underlying reason the pressure appears is the same. From this picture, Reynolds derived an equation, it carries his name to this day, that relates the pressure in a thin film to the geometry of the gap, the speed of the surfaces, and the viscosity of the fluid. It remains the governing equation of fluid-film lubrication. It is what is being solved, in some numerical form, whenever a modern engine bearing or turbine bearing is designed. Reynolds was not entirely alone in the field. In Russia, Nikolai Petrov had approached the friction of lubricated bearings from the theoretical side and published in 1883, the same year as Tower's first report, deriving an expression for the viscous friction in a lightly loaded journal bearing that is still taught under his name. Petrov saw clearly that the friction in a well-lubricated bearing was the friction of a liquid, not of two solids. What he did not do was extend the insight to explain how the film carries the load. That step belonged to Tower's accident and Reynolds's analysis. The theory was then extended. In 1904, Arnold Sommerfeld produced a closed-form solution of the Reynolds equation for a long journal bearing, giving designers usable expressions for pressure distribution and load capacity. Around the same period, Richard Strybeck, working in Germany, ran extensive friction measurements on bearings, and the curve that came out of that work organized the entire subject. The Strybeck curve is worth understanding because it explains something every mechanic has observed without necessarily having a name for it. Plot the friction in a lubricated bearing against a quantity combining viscosity, speed, and load, and you do not get a straight line, you get a valley. At the right-hand side, high speed, thick oil, light load, you are in full fluid film lubrication. The surfaces are completely separated. Friction here is purely the internal friction of the liquid being sheared, and it rises gently as speed increases, because faster shearing takes more work. Move left, and the film gets thinner. At some point it becomes comparable to the height of those surface asperities we discussed earlier, and the peaks start to touch through it. This is the mixed regime, and friction climbs. Keep going left. Low speed, heavy load, hot thin oil, and the film essentially collapses. The load is carried by the high points, protected only by whatever molecular layer of lubricant is chemically clinging to the metal. This is boundary lubrication, and it is where friction and wear are worst. The practical consequence is this: the most dangerous moment in the life of a plain bearing is not when the machine is working hardest. It is the moment of starting. At zero speed there is no wedge, no pressure, no film. Every start drags the bearing left across the Strybeck curve into the boundary regime and back out again. Which means that the film Reynolds had explained, elegant as it was, could not be the whole answer. Something had to protect the metal in the seconds before the film formed, and something had to work in the places where a fluid film could never form at all. Those two questions would take most of the next century. Let us go back to that freight train. By the time Reynolds published, the theory of the fluid film existed on paper in Manchester. Out on the line, in the dark, none of that had reached the men doing the work, and it would not reach them, in any form they could act on, for a long while. What they had was a steel box, a brass block, a fistful of oily waste, and their own senses. The arrangement is worth taking apart, because it is the most widespread bearing in the history of transport, and almost nobody under a certain age has seen one working. Bolted into the side frame of the truck is the journal box, a cast steel housing with a hinged lid on the outboard face. The axle end passes into it. The last few inches of that axle, the journal, are turned and polished to a mirror finish. Resting on top of the journal, not around it, is the bearing itself, a curved block, usually bronze, with a thin layer of Babbitt metal cast onto its underside. Above the brass sits a steel wedge, or shim, that transmits the weight of the car down through it. The bearing carries the load from above. It does not enclose the axle. Below the journal, filling the bottom of the box, is the packing, cotton or wool waste, or in later practice, braided woolen yarn, saturated with oil. The system works by contact and capillary action. The underside of the journal dips into the oil-soaked packing on every revolution, picks up a film, and carries it around into the loaded region under the brass, where, if everything is right, Reynolds's wedge forms, and the car rides on liquid. The lid keeps out grit and rain. The oil in the packing is the reservoir, and it has to be topped up, and the packing itself has to be tamped down into place and eventually replaced. There were two ways this failed. The first was simple starvation. Oil leaks, oil is consumed, and a box that was not serviced would eventually run dry. That was a maintenance failure, and it was manageable. The second was more insidious, and men who worked around freight cars had a name for it: a waste grab. If the packing was allowed to stand too high, or if a loose strand worked free, a thread of that waste could be caught by the turning journal and dragged up into the gap between journal and brass. Once a strand went in, it pulled the rest after it. The packing wound itself around the axle. And the moment that happened, the oil supply to the loaded surface stopped, because the reservoir was no longer down in the bottom of the box. It was wrapped around the shaft. The film broke. The temperature climbed. The oil began to smoke, and then the oily waste caught, and there was a fire burning under a moving railroad car. The defense was inspection, and inspection meant people. Yard crews went down the length of a train opening lids, checking oil levels, tamping packing back into position, adding oil at major stops. Train crews watched from the caboose and the head end. Men stationed along the line watched trains pass in the dark, looking for the glow, and at some railroads called out that a train was clear when they had seen nothing. Note what those men were doing. They were monitoring the condition of a hydrodynamic oil film, a thing Osborne Reynolds had described mathematically, by smell and by eye, from 30 feet away, at speed. There is a great deal of practical engineering knowledge that exists in exactly this form and has never been written down. Two things eventually retired the practice. The first was instrumentation. Railroads began installing hot box detectors beside the track, infrared scanners that measured the temperature of every bearing on every passing train and signaled the crew if one was running hot. This mattered because the human method had a built-in delay. By the time smoke appeared, the bearing was usually already far along toward a burned-off journal. The second was the roller bearing, which arrived on freight cars in earnest through the middle decades of the 20th century and steadily displaced the plain journal. This is where our previous episode and this one meet. It is tempting to describe that transition as rolling motion defeating sliding motion, and there is something in it, but the honest account is that the roller bearing won on maintenance. A sealed roller bearing unit carries its own grease, keeps out contamination, and does not require a man with a can and a lantern. The rolling elements dip into a small quantity of oil or run in grease, and they are left alone. The bearing did not eliminate the film, it enclosed it and put the responsibility for keeping it there onto the lubricant and the seal rather than onto a person, which raises the question that governs the next stage of this history. If a lubricant is going to be sealed inside a bearing and expected to stay there for years, then a liquid that will run out of any opening it can find is the wrong material. You need something that stays. Think about a front wheel bearing on a car, or a universal joint under a truck, or the sealed bearing in an electric motor. None of these can hold a bath of oil. There is no reservoir, no sump, no pump, and in most cases, the bearing is not even horizontal. Put liquid oil in, and it will find the lowest point and leave. The answer is a material that behaves like a solid until you disturb it, and then behaves like a liquid. Grease is often described as thick oil, and that description is wrong in a way that obscures how clever it is. Grease is not oil that has been thickened in the sense of being made more viscous. Grease is ordinary lubricating oil held inside a sponge. The sponge is made of soap. Take a fatty acid, react it with a metal hydroxide, and you get a metallic soap, the same basic chemistry as the soap in a bathroom, but made with the wrong metal for washing and the right metal for engineering. Cook that soap into hot oil in the correct way, and it does not dissolve. It crystallizes out as a mass of microscopic fibers, tangled together into a three-dimensional network, and the oil is trapped in the spaces between those fibers by surface tension. At rest, the network holds. The grease sits in the bearing housing and does not flow. Under shear, when the rolling elements pass through it, the network yields locally and releases oil into the contact. When the shearing stops, it recovers and holds the oil again. This behavior has a name, and the name is worth knowing because it appears in many places. The material is shear thinning. It is stiff when undisturbed and fluid when worked. A grease gun relies on it. So does the ability of a wheel bearing to hold its lubricant on a hillside in July. The consistency of the finished product is graded on a scale set by the National Lubricating Grease Institute, running from very soft, almost pourable grades up to block greases stiff enough to hold their shape. That grading measures how far a standard cone sinks into the sample, which is a delightfully direct way to measure something. The other number that matters is the dropping point, the temperature at which the soap structure lets go and the grease releases its oil. Exceed it, and the sponge collapses. The oil runs out, and what remains in the housing is dry soap, which lubricates nothing. And that number is where the history lives, because the choice of metal in the soap determines it. The earliest industrial greases were thickened with calcium soaps, lime soaps. Calcium grease has an excellent property. It is highly resistant to water. Wash it, splash it, submerge it, and it stays put. That made it the right material for wheel bearings, farm equipment, mining machinery, anything working in mud and rain. But traditional calcium greases had a low dropping point. Warm them past a fairly modest temperature, and the structure failed. Sodium soaps, soda-based greases, went the other way. They tolerated higher temperatures well, but sodium soap is water-soluble, which is exactly what you would expect from something chemically closer to real soap, and a soda grease exposed to water would wash out or emulsify into a useless paste. So the industry had two greases, each good at precisely what the other was bad at, and lubrication engineers spent decades choosing between them, application by application. Aluminum soaps offered another set of trade-offs. None of them solved the problem. They distributed it. The resolution came from a metal that had almost no industrial use at the time. On March 3, 1942, an American chemical engineer named Clarence E. Earle was granted United States Patent 2,274,675, titled Lubricant Containing Lithium Salts. It was one of a small group of related patents he obtained, and it is the first description in the patent literature of a grease thickened with simple lithium soaps. Lithium soap turned out to do both jobs. It has the water resistance of a calcium grease and the temperature tolerance of a sodium grease. On top of that, it holds up well mechanically. It resists being broken down by prolonged working, and it pumps properly through a grease line, which matters more than it sounds when you are trying to service a machine through a fitting. It costs more to manufacture than calcium or sodium grease. It was adopted anyway because the performance was worth the difference, and lithium soap greases, particularly formulations based on lithium 12-hydroxystearate, took a very large share of the market. A National Lubricating Grease Institute production survey found that a substantial majority of grease sold worldwide is thickened with either simple lithium soap or a lithium complex. And that word complex introduces one of the most instructive delays in this entire history. On March 18, 1947, 5 years after Earle, Lester W. McLennan was granted patent 2,417,428, one of the first patents describing a complex soap grease. A lithium complex adds a second, smaller acid into the soap structure, and the result has a significantly higher dropping point than simple lithium grease. It works hotter. For applications where temperature is the limit, it is straightforwardly better. It did not sell, not in 1947, Not in the 50s, not in the 60s. Lithium complex greases did not enter the market in serious volume until the early 1980s, when they began displacing the simple lithium greases that had been the industry's mainstay for 30 years. 35 years between the patent and the adoption. This is worth sitting with, because it is the pattern that governs most of the history we are following. A patent is a legal document recording that somebody described an idea. It is not evidence that the idea worked in service, that anyone could manufacture it economically, that customers wanted it, or that the machines of the day needed what it offered. Those are four separate hurdles, and they are cleared at different times, sometimes decades apart. McLennan's grease was waiting for machinery hot enough to require it, and for a supply chain willing to make it. There is one more piece of grease history that belongs here, because it is in every workshop drawer in the world. The grease fitting, the little nipple with a spring-loaded ball in its nose that you press a grease gun onto, is a small piece of design that solved a large problem. It lets grease in, under pressure, and closes immediately behind it, keeping out dirt and water. The most common pattern is universally called a Zerk fitting after Oscar Zerk, and the arrangement of gun and fitting turned greasing from a job requiring the machine to be opened into a job requiring nothing but a few seconds and a pump handle. Grease solved the problem of a lubricant that stays where it is put. It did not solve the problem underneath, which applies equally to oil and to the oil held inside grease. Both of them are made of hydrocarbon molecules. Both of them, in a hot machine, in the presence of air, begin to change. Open the crankcase of an engine that has been running on plain mineral oil for a long time, and you will find a museum of chemistry. There will be sludge, a dark, soft deposit collecting in the low places and in the corners. There will be varnish on the hotter surfaces, a hard amber film that will not wipe off. There will be lacquer around the piston rings, gumming them into their grooves so they no longer press outward properly. And there will be acid, quietly attacking bearing surfaces. None of this comes from dirt getting in. It is the oil itself, changing. The reaction is oxidation, hydrocarbon molecules in the presence of oxygen and heat, especially with metal surfaces acting as catalysts, react to form new compounds, organic acids, and larger molecules that will not stay dissolved. Raise the temperature and the rate climbs steeply. Every engine, by design, holds a thin film of oil against the hottest surfaces it possesses. An internal combustion engine adds a second source of contamination that a steam engine never had. Combustion is never perfect. Unburned fuel, water, and soot blow past the piston rings into the crankcase and end up in the oil. The oil in a running engine is not a clean fluid in a clean container. It is a fluid that is being continuously poisoned. Through the 1920s, the response was procedural: change the oil often, and accept that engines would need decarbonizing. It worked, in the sense that it kept engines alive. It also meant that lubricant quality was fundamentally limited by the chemistry of what came out of a still. The change arriving through the 1930s and accelerating through the 1940s was the realization that you could deliberately put things into the oil that were not lubricants at all. The first family of these were the detergents and dispersants, and they are widely misunderstood because of what the words suggest. A detergent additive does not clean an engine the way soap cleans a pan. What it does is neutralize the acidic products of combustion and oxidation, and keep deposit-forming material from adhering to hot surfaces in the first place. That neutralizing capacity is measurable. It is the reason engine oils carry a total base number, and it is consumed as the oil works, which is one of the real reasons oil has a service life. A dispersant does something subtler, and if anything, more important. Soot and oxidation products in a used oil are solid particles, and solid particles in a liquid want to find each other, clump together, and settle out as sludge. A dispersant molecule has one end that attaches to a particle and another end that is comfortable in oil, so it surrounds each particle and keeps it suspended and separated. Which means that the oil in a well-formulated engine gets dirty on purpose. A modern diesel oil at the end of its service interval is black, and it is black because it is holding an enormous quantity of soot in suspension where it can do no harm, rather than allowing it to collect somewhere it can. Black oil is not necessarily failed oil. That is a genuinely counterintuitive fact, and it is worth knowing. Then there is the additive that matters most for the survival of moving parts, and its history is a small masterpiece of accident. Zinc dialkylthiophosphate, universally abbreviated ZDDP, was introduced into engine oils in the late 1930s, and three companies, Lubrizol, American Cyanamid, and Union Oil, filed patents around 1941 covering its use. What they were claiming was its value as a corrosion inhibitor and an antioxidant. That is what it was sold as. That is what it was in the oil to do. Through the 1940s, nobody appeared to notice that it did anything else. Then, in 1949, the American automobile industry began introducing V8 engines with overhead valves and higher compression ratios. The valve train in such an engine works considerably harder than in the older designs. The camshaft lobe pushes directly against the follower, and at that interface you have a small, heavily loaded contact with very little sliding speed, which is precisely the left-hand end of the Strybeck curve. Boundary lubrication, no fluid film worth the name. The results were severe. Cam and follower wear became a widespread problem across the United States through the early 1950s, with engines wearing out valve trains long before anything else on them was worn. In 1955, investigating the problem, engineers found that oils containing ZDDP produced markedly less wear than oils without it. Why it worked was not obvious then, and took a long time to establish properly. The current understanding is that under the pressure and temperature of a rubbing contact, ZDDP decomposes and reacts with the metal surface to build up a tenacious film, a tribofilm, glassy and phosphate-rich, that adheres to the steel. That film is softer than the steel underneath, and it is sacrificial. When two asperities meet, they shear the film, rather than welding to each other. The film is worn away and continuously rebuilt from the additive still in the oil. It is chemical armor, generated in place, exactly where it is needed, and only where it is needed. The adoption was rapid. By 1958, ZDDP was described as having become standard in high-quality motor oils, and it has remained in essentially every engine oil since. One of the leading researchers in the field has called it arguably the most successful lubricant additive ever invented, on the grounds that decades of concerted effort have not produced a cost-effective replacement. An additive introduced for one purpose, whose principal virtue went unnoticed for roughly 15 years, and which was then discovered because an entire industry's camshafts were wearing out. There is a distinction here that experienced people will expect, and it is worth drawing. ZDDP is an anti-wear additive. It is not an extreme pressure additive, though the two are often confused. Extreme pressure additives, typically sulfur and phosphorus compounds, are designed for far more brutal conditions, most notably hypoid gears, and they work by chemically reacting with the metal surface to form a soft compound that shears away before the metal can weld. They are aggressive by design, aggressive enough that some of them will attack yellow metals like bronze, which is why gear oil and engine oil are not interchangeable. Anti-wear additives are gentler. Different problem, different weapon. Alongside these came a supporting cast that rarely gets discussed. Antioxidants that intercept the oxidation reaction before it propagates, rust inhibitors that protect surfaces during shutdown when condensation forms, antifoam agents because oil whipped by a crankshaft entrains air and foam is compressible and will not carry a load, friction modifiers, which came later and are the reason a modern oil can save measurable fuel. By the 1950s, a can of motor oil was no longer a refined natural product. It was a formulation, base oil plus an engineered additive package, in which the additives might account for a substantial fraction of the volume, which created a new problem, and it was a problem of information. If oil is now a designed product with widely varying properties, how does a person standing in a shop know what they are buying? Before there were numbers, there were adjectives. Oil was sold as light, medium, heavy, extra heavy. The trouble was that these words meant whatever the company printing them wanted them to mean. The same barrel of oil could be marketed as a heavy automobile oil by one firm and a light tractor oil by another, and there was no external standard to appeal to. The terms were bound up with trademarks and advertising, and attempts to get the large oil companies to agree on what they signified went nowhere. The Society of Automotive Engineers, founded in 1905, took the problem up, and in June 1911 published a specification for automobile engine lubricating oil, the first formal specification of its kind. Out of that effort came a scheme of numbered grades. Instead of arguing about adjectives, measure how fast the oil flows through a standard orifice at a standard temperature, and put the resulting number on the can. The grades ran 10, 20, 30, 40, 50, with a sixth added later, and the system eventually took the designation it still carries, though that name came decades after 1911, and it is worth not backdating it. The numbering was a genuine advance, and it exposed a genuine limitation, which is that a single number describes an oil at a single temperature. Viscosity is not a fixed property. Every liquid gets thinner when heated, and mineral oils get thinner rather dramatically. An oil that is correct in a hot engine is stiff at dawn in January. An oil that will let you crank the engine in January is dangerously thin once the engine reaches operating temperature. The period solution was seasonal. You ran a thinner grade through the winter and drained it in spring for something heavier. Anybody who kept a car through the 1930s and 1940s did this, and the shops did a steady trade in it. It was a nuisance, and in a cold snap it could be worse than a nuisance. An oil too stiff to be drawn up a pickup tube will starve an engine in the first seconds after starting, which are already the worst seconds it faces. Winter grades were formalized with a W designation, defined by viscosity, measured at low temperature rather than at operating temperature. That gave two separate scales for two separate questions. The W number describes cold behavior, the plain number describes hot behavior. And that separation opened the door to solving the problem outright. The tool was a class of additives called viscosity index improvers, and the mechanism is genuinely elegant. They are long polymer molecules dissolved in the oil. When the oil is cold, these molecules coil up tightly on themselves and take up little space, so they have almost no effect on how the oil flows. As the oil heats, the coils relax and open out, sprawling through the fluid and getting in each other's way, which resists flow and props up the viscosity just as the base oil is losing it. The additive fights the temperature, and it fights hardest exactly where help is needed. Start with a base oil thin enough to satisfy a cold cranking requirement. Add enough of the right polymer to satisfy the hot requirement, and you have an oil that passes both tests. That is what a multigrade is. A 10W30 is not two oils, and it is not an oil that changes grade. It is a single fluid that meets the low temperature specification of a 10W and the high temperature specification of a 30. Multigrades reached the market in earnest in the late 1950s, and the seasonal oil change quietly disappeared from ordinary practice. The trade-off, which mechanics have argued about ever since, is that those polymer coils are physically vulnerable. Dragged repeatedly through the shearing violence of a bearing or a gear mesh, they can be temporarily flattened out of the way, which momentarily lowers viscosity right where it matters, and over time they can be cut into shorter fragments that no longer do the job at all. An oil that has sheared down permanently is no longer the grade printed on the can. This is a real phenomenon, and it is one reason oils are tested for shear stability rather than trusted on formulation alone. Viscosity was only half of what a buyer needed to know. The other half was what the oil was made to survive, and that came from a parallel effort, service classifications, developed with the American Petroleum Institute, which sorted oils by the kind of duty they were qualified for rather than by how thick they were. An oil for a hard-working diesel and an oil for a mild gasoline engine might carry the same viscosity grade and be entirely unsuited to each other's job. Together, the two systems did something rather profound and rather unglamorous. They made it possible for a person with no chemistry and no laboratory to walk into a store, read two markings, and buy the correct fluid for their machine. But every one of these oils, however carefully graded and however heavily dosed with additives, was built on molecules that had been made underground over geological time. Crude oil is a mixture. It contains molecules of many shapes and sizes, and refining can sort and clean that mixture, but it cannot fundamentally change what is in it. The next question was obvious, and by the time anyone got serious about asking it, there was a war on. Germany in the 1930s had coal and did not have oil. That single fact drove an enormous national research effort across fuels and chemicals, and lubricants were part of it. If a country cannot rely on importing crude, and if its machinery nevertheless has to run, then the question becomes whether lubricating oil can be built up from smaller molecules rather than distilled out of a natural mixture. Hermann Zorn, working in the German chemical industry, took up the problem, and his framing of it was not merely substitutional. He was not only asking how to replace mineral oil, he was asking whether one could keep the useful properties of mineral oil while discarding its inherent defects, the tendency to thicken and refuse to flow at low temperature, the tendency to form gum and deposits, the poor resistance to oxidation at high temperature. The insight underneath is worth stating plainly, because it applies to the whole field. A refined mineral oil is a population. Even after the most careful processing, it contains a distribution of molecular shapes and sizes. Some of those molecules are excellent lubricants. Some are waxy and will crystallize in the cold. Some have chemical structures that oxidize readily and start the sludge cascade. The overall performance of the oil is set not by its best molecules, but by its worst ones, because the worst ones are what fail first. If instead you build the molecule you want from scratch and make a fluid consisting almost entirely of that one molecule, there are no worst molecules. The distribution collapses to a point. Zorn's group pursued esters, molecules formed by reacting an alcohol with an acid, and worked through a very large number of candidate structures, testing diesters and polyol esters, drawing feedstocks from coal chemistry and from Fischer-Tropsch synthesis. Figures of several thousand esters evaluated during the war years appear widely in industry accounts, and while the exact number is difficult to verify from independent sources, the scale of the program is not in doubt. A parallel and smaller effort ran in the United States at the Naval Research Laboratory between 1942 and 1945, and it produced the first diester synthetic base oils on the American side. You will often hear this history compressed into a dramatic claim that German engines seized in the Russian winter because their oil gelled, and that this defeat drove the synthetic program. Wartime cold certainly caused enormous mechanical difficulty, and lubricant behavior at low temperature was a real and pressing problem. But the German synthetic lubricants effort was underway well before the Eastern campaigns, driven by the structural fact of having no domestic crude. It is one pressure among several, and single-cause explanations of this kind rarely survive contact with the documents. What genuinely established synthetics as a category after the war was not the automobile at all. It was the jet engine. A turbine engine imposes conditions that mineral oil simply cannot meet. The bearings sit close to a combustion section. The oil is expected to work continuously at temperatures that would cook a petroleum oil into varnish within hours, while remaining fluid enough at high-altitude cold soak to circulate at startup. The temperature span is enormous, and both ends of it are extreme. Ester-based synthetics could do it. Polyol esters in particular, developed and patented in the late 1950s in work involving Drew Chemical and Mobil Chemical, became the basis of turbine engine oils, and aviation has run on synthetic lubricants ever since. If you have flown, you have been carried by machinery, lubricated with fluid that was designed rather than discovered. The other major synthetic family took a different route. Polyalpholefins, universally called PAO, are made by taking small hydrocarbon molecules and polymerizing them into larger ones of a controlled, uniform, branched structure. The result is chemically a hydrocarbon. It is not an ester, but it is a hydrocarbon of one deliberate shape, with no wax, no sulfur, no nitrogen, and none of the reactive structures that crude oil carries as a matter of course. It has an unusually high viscosity index and a very low pour point, which is another way of saying it changes less with temperature than anything that comes out of the ground. The move into the automotive market came in the 1970s, and the two claims that dominate the retelling both come from companies with an interest in the answer. Amsoil, founded by a former fighter squadron commander who had watched synthetics work in jet engines, put a synthetic motor oil on the market in 1972 and states that it was the first to meet American Petroleum Institute service requirements. Mobil introduced Mobil 1 based on PAO with an ester component, and brought it to the wider market in 1974. Both accounts are corporate, both are contested at the margins, and the useful summary is that a small independent and a very large oil company arrived at the same conclusion within about 2 years of each other, and that the oil price shocks of the period gave the argument for a longer-lasting, more efficient lubricant, a commercial force it had previously lacked. The reception among mechanics was frosty for a long while, and that reaction was not unreasonable. Synthetic oil cost several times what conventional oil cost. Its advantages showed up mainly at temperature extremes and over long intervals, neither of which is easy to see in a driveway, and claims of extended drain intervals sat badly with an industry organized around selling oil. It took roughly 2 decades for synthetics to move from the margins to the mainstream, and they did so largely because engines changed underneath them. Turbochargers, tighter packaging, higher operating temperatures, longer manufacturer-specified service intervals, until the conditions that synthetics were designed for became ordinary conditions. There remains, however, a set of places where no liquid of any kind will survive. Put a conventional oil in a vacuum and it evaporates. Put it next to a furnace and it decomposes. Freeze it hard enough and it stops flowing. Expose it to intense radiation and its molecules come apart. Put it in a food processing plant and it becomes a contamination problem. Seal it inside a mechanism that will never be opened again for 40 years, and you are asking a great deal of it. For all these cases, the answer is to abandon the fluid film entirely and use a solid that is slippery in itself. The physics rests on crystal structure. Certain materials are built in layers, sheets of atoms bonded strongly within the sheet, and bonded only weakly to the sheets above and below. Under shear, the sheets slide over one another at very low force, while each sheet remains intact. The material provides its own internal plane of weakness, and that plane is where the sliding happens instead of at the metal surface. Graphite is the familiar example, and it is old. Graphite from the Borrowdale deposit in England was used for lubrication in locks and mechanisms in the 16th century, often mixed with pig tallow, and powdered graphite has been a workshop staple ever since. A locksmith's puffer bottle is a direct descendant of that practice. But graphite carries a hidden dependency that took a long time to identify, and it is one of the genuinely surprising facts in this subject. Graphite is not intrinsically slippery. Its low friction depends on molecules of water vapor adsorbed from the atmosphere onto the edges of its layers. Those adsorbed molecules are part of the mechanism, and without them, the layers do not slide easily. Take graphite into a vacuum and hold it there. The adsorbed moisture is drawn away, and the graphite stops lubricating. It becomes abrasive. The material that had been protecting the surface starts destroying it. This was discovered the way such things usually are, by equipment failing at high altitude and in vacuum chambers, at a point when a great many people had assumed graphite was universally reliable. Its replacement had been sitting in plain sight, misidentified, for centuries. Molybdenite is a naturally occurring mineral, molybdenum disulfide, and it looks so much like graphite, gray-black, metallic, greasy to the touch, that early users routinely mistook one for the other. Both were used for lubrication before the Industrial Revolution, and in a number of cases people who thought they were applying graphite were applying molybdenite. As one survey of the field observed, it was a good choice made for the wrong reason. Molybdenum disulfide has the same layered structure and the same easy shear between layers, but it does not need adsorbed water. If anything, it performs better in the absence of atmosphere, in a vacuum, in dry gas, in oxygen-free environments. Its friction is lower than in ordinary air. The material became practically available because of metallurgy rather than tribology. Methods of purifying molybdenum disulfide and extracting molybdenum were developed late in the 19th century, and demand for molybdenum as a steel alloying element during the First World War led to the development of the Climax mine in Colorado, which began production in 1918 and ran for the better part of the century. With high-purity material available in quantity, its lubricating properties were investigated seriously through the late 1930s and 1940s, and those investigations demonstrated its stability under extreme contact pressure and in vacuum. The National Advisory Committee for Aeronautics, NASA's predecessor, began research on aerospace applications in 1946. The result is that a great deal of hardware in orbit runs on a black powder that a 16th century locksmith would have recognized and misnamed. A third material arrived from a different direction entirely. Polytetrafluoroethylene, PTFE, was first synthesized at DuPont in 1938, and its remarkably low friction against most materials made it useful as a solid lubricant and as a component of bearing materials. It is not layered in the same way. Its slipperiness comes from the character of the fluorine-carbon surface, which does not want to interact with anything. In filled forms, combined with glass fiber or bronze or graphite for strength and wear resistance, it became a standard material for plain bearings that must run dry. In practice, these materials are applied in several ways: as loose powder, as an additive suspended in oil or grease, providing a reserve of protection for the moments when the fluid film fails, which is why molybdenum disulfide turns up in assembly lubricants and in gear oils, or as a bonded film, the solid lubricant mixed with a resin binder, sprayed onto the part and cured, producing a permanent gray-black coating that lubricates for the life of the component without any servicing at all. Bonded films have a specific and unglamorous virtue that matters enormously in industry. They prevent galling, the tearing and seizing that occurs when two similar metals, particularly stainless steels, are slid or threaded together under load. Anyone who has ever seized a stainless bolt into a stainless nut and had to cut it out has met the problem that a bonded solid film exists to solve. So we now have three families: oils, greases, and solids. Theory to explain the film, chemistry to keep the oil alive, and standards to describe what is in the can. And yet one enormous question was still unanswered, and it concerned machinery that the entire industrial world depended on. Because by the calculations then available, gears should not work. Take Reynolds' theory and apply it to a pair of gear teeth in mesh, and it gives you an answer that is plainly wrong. The difficulty is geometric. In a journal bearing, the shaft and the bearing have nearly the same curvature. The surfaces conform to one another, wrapping around across a broad area, and the load is spread out. That is exactly the situation Reynolds analyzed. Gear teeth do not conform. Two convex surfaces touch along a line, and the load, which may be considerable, is concentrated onto that line. The contact pressures are extraordinary, far beyond anything in a plain bearing. The same is true of a rolling element bearing, where a hardened ball presses against a raceway across an area smaller than a pinhead. Feed those numbers into the classical equations, and you get a predicted oil film thickness, so small that it is less than the height of the surface roughness on the parts. In other words, the theory says the film cannot possibly separate the surfaces. The asperities must be in continuous contact. Every gearbox should be tearing itself apart. Gearboxes were not tearing themselves apart. They were running for decades. Rolling bearings were achieving fatigue lives that made no sense if the elements were rubbing directly on the races. This discrepancy sat in the literature from the 1920s onward, and it was not a small anomaly. It was a hole in the middle of the subject, right underneath the most heavily loaded machinery in existence. The resolution required two effects, and it required taking both of them seriously at once. The first is that steel is not rigid. It is very stiff, but under the pressures at a gear contact, it deflects measurably. The ball flattens slightly against the raceway. The tooth surfaces flatten against each other. That elastic deformation spreads the load over a larger area than a point or a line, which lowers the pressure and, crucially, creates a small region of nearly parallel surfaces where a film has somewhere to exist. The second effect is the one that makes the whole thing work, and it is remarkable. The viscosity of oil is not constant with pressure. Squeeze an oil hard, and it becomes dramatically more viscous, not by a few percent, by orders of magnitude. At the pressures inside a gear contact, the lubricant passing through behaves less like a liquid and more like a soft solid. For the fraction of a millisecond it spends in the contact, it is effectively glass. Now put the two together. The oil is dragged toward the contact. As it approaches, the pressure begins to rise, and the rising pressure stiffens the oil enormously. By the time it reaches the narrowest part of the gap, it has become so viscous that it cannot be squeezed out sideways in the time available. It is trapped, and being trapped and incompressible, it pushes the surfaces apart, and the surfaces, being elastic, give way. The film survives because the oil hardens under the very pressure that was supposed to destroy it. This is elasto-hydrodynamic lubrication, EHL, in every textbook and every bearing catalog since. The theoretical history runs through several countries. Ertel, in 1939, was the first to bring elastic deformation and pressure-dependent viscosity into the analysis of the inlet region. In 1949, A. N. Grubin published the treatment that carried the idea into general circulation, combining Reynolds's hydrodynamics with Hertz's contact mechanics, and producing an approximate solution that predicted film thicknesses vastly larger than the old theory, and consistent with machines that actually worked. In 1951, A.I. Petrusevich obtained a full numerical solution for line contact and found a curious feature, a sharp spike of pressure right at the exit of the contact, which is still sometimes named after him. Through 1959 and into the 1960s, Duncan Dowson and G. R. Higginson at Leeds produced systematic numerical solutions and, from them, practical formulas for film thickness, the work collected in their 1966 book on the subject. The scale of what they were describing deserves a moment. The film in a well-lubricated rolling bearing under load is commonly a fraction of a micrometer thick, smaller than a wavelength of visible light. It is renewed thousands of times a minute. It exists for microseconds at any given point on the raceway, and the entire load path of a machine, a wind turbine gearbox, a car's final drive, a machine tool spindle, passes through it. There is one more consequence, and it is the one every maintenance engineer, eventually learns. Whether a bearing or a gear is genuinely separated depends on the ratio between that film thickness and the roughness of the surfaces, which means surface finish is not cosmetic. A raceway polished to a finer finish requires a thinner film to achieve separation and can therefore run on thinner oil, or slower, or hotter, and still survive. The precision revolution and the lubrication revolution turn out to be the same revolution, approached from opposite ends. Making the surface smoother and making the film thicker are two ways of accomplishing one thing. By the middle of the 1960s, then, the intellectual structure was complete. Hydrodynamic lubrication, boundary lubrication, mixed lubrication, elasto-hydrodynamic lubrication, oils, greases, solids, additives, synthetics. What the subject did not have was a name. In 1964, the British Department of Education and Science convened a working group. The question put to it was administrative rather than scientific. How was lubrication being taught in Britain? What research was being done? And what did industry actually need? The group was chaired by Dr. H. Peter Jost, an engineer who had come to Britain from Berlin as a young man, trained through apprenticeships, and spent his career in the lubricants industry. The working group did something more interesting than answer the question asked. They observed that the subject had no boundaries because it had no identity. Friction, wear, and lubrication were being studied in mechanical engineering departments, in physics, in chemistry, in metallurgy, in materials science, everywhere and nowhere, with no common vocabulary and no sense of belonging to a single field. Brakes and clutches were one subject, bearing design was another, surface chemistry a third. Nobody was responsible for the whole. So they proposed a word. From the Greek root meaning rubbing, they made tribology and defined it as the science and technology of interacting surfaces in relative motion and of related subjects and practices. They also, on the advice of a senior civil servant, put a number on it. Working with the marketing department of a large oil company, they estimated what British industry could save simply by applying knowledge that already existed. The lowest figure in the range they developed, and they deliberately chose the lowest, was £515 million a year. The report went to the minister in October 1965, 9 months after work began, and was published as a government report on the 9th of March 1966. It landed. Similar studies followed in the United States, in Canada, and elsewhere, and they came to broadly similar conclusions that the cost of friction, wear, and corrosion runs at somewhere in the region of 1% of a developed economy's output, and that a large part of that is avoidable. There is something worth noticing in the shape of this. The activity is 4,000 years old. There is a painting of it in a tomb at Deir el-Bersha. Leonardo measured it. Tower found the pressure in it. Reynolds wrote its equation. Every industrial economy on Earth depended on it entirely, and it was 1966 before anyone gave it a name. That is the characteristic condition of the subject. It is not that lubrication is unimportant. It is that it is invisible. It works by preventing things from happening, and prevention leaves no evidence. A bearing that runs for 20 years and is then quietly scrapped has an uneventful history. Nothing about it will ever be written down. The word helped. A little. Not enough that most people have heard it. The last chapter of this story is about constraints arriving from outside engineering, and about what happens when a lubricant is asked to serve two masters. Begin with the whales, because we left them unfinished. Sperm oil never quite went away. Its chemistry, those wax esters, stable under heat, resistant to rust, effective in thin films, turned out to be difficult to match, and one place it persisted was in automatic transmission fluid. A transmission is a demanding environment. It needs a fluid that lubricates gears and bearings, transmits torque through a converter, and controls the friction of clutch packs with precision, all while running hot. Sulfurized sperm oil did all of that unusually well, and it was cheap and plentiful, which meant the incentive to find something better was weak. Then it stopped being available. The sperm whale was included in American Endangered Species Protection at the end of the 1960s, and in December 1970, a ban took effect on imports of oil, meat, and other products from sperm whales and 7 other species. At the time of the ban, American consumption of sperm oil ran at something like 40 to 50 million pounds a year, and roughly half of that was going into lubricants, transmission fluids, gear oils, metalworking oils, tractor hydraulic fluids. The industry had to replace it quickly, and there had been little research to build on, precisely because the natural product had been so satisfactory. 2 approaches were tried. One was to synthesize something with a similar molecular character. The other was to find a natural equivalent, and there was one, growing in the deserts of the American Southwest and northern Mexico. The jojoba shrub produces a seed oil that is not a triglyceride, but a liquid wax ester, chemically close to sperm oil, and it was pursued intensively as a substitute. A patent literature grew up around jojoba derivatives aimed specifically at replacing sulfurized sperm oil. The obstacle was price. Jojoba was expensive, and remained so. You will frequently encounter a dramatic statistic attached to this episode, that transmission failures in the United States exploded from under 1 million a year before 1972 to over 8 million by 1975. It appears in a great many places. It originates in the marketing material of a company selling transmission fluid additives, and it should be treated accordingly. That the transition caused real difficulty is not in doubt. That particular number does not have independent support. The second outside constraint came from the exhaust pipe, and it put lubrication chemistry directly at odds with itself. Catalytic converters clean exhaust gases by passing them over precious metal catalysts. Those catalysts are vulnerable to poisoning, and one of the things that poisons them is phosphorus. A small quantity of engine oil is burned in normal operation. This is unavoidable since the cylinder wall must be oiled, and the combustion products go out through the converter, which means the phosphorus in ZDDP, the most effective anti-wear additive ever found, gradually degrades the emissions control system. The response was regulatory and incremental. Successive American Petroleum Institute service categories capped the permitted phosphorus level, tightening over time. The category introduced in 1995 allowed up to 1,200 parts per million, and the category introduced in 2010 allowed 800. This is the origin of a debate that runs through every classic car club in the English-speaking world. Older engines with flat tappet camshafts, the very design whose wear problems caused ZDDP to be adopted in the first place, were developed alongside oils containing much more of it. Owners of those engines argue, with some justification, that modern low-phosphorus oils are not what their camshafts were designed to run on, and specialist high zinc oils exist for exactly this market, generally outside current specifications. The engineering answer for new engines was to design the problem away, roller followers instead of sliding ones, which changes that contact from sliding to rolling and moves it out of the boundary regime. The old solution and the new solution are the same solution our first episode described, applied to a different place in the machine. The third constraint is fuel economy, and it pushes in an uncomfortable direction. Some of the energy an engine produces is spent shearing its own oil. Thinner oil takes less energy to pump and less to shear, so a thinner oil returns measurably better fuel consumption across a fleet. This is why grades have marched steadily downward over the past few decades, from 20W50 as an ordinary passenger car oil to 10W30 to 5W20 to 0W16 and thinner still, with new low-viscosity grades added to the classification. But the film thickness that separates the surfaces depends directly on viscosity. Thin the oil, and you thin the film, and you move every contact in the engine leftward along the Strybeck curve, closer to the region where asperities touch, which is why modern engine oils are extraordinary pieces of chemistry. They are being asked to be thin enough to save fuel and robust enough to protect surfaces that the thinness has left exposed. A job done through additive chemistry, through friction modifiers, and through the surface finishes now achievable in production. Every drop of that margin has been argued for. And now the machinery itself is changing again. An electric drive unit has no combustion, no soot, no fuel dilution, and no acids. In that sense, the lubricant's life is easier, but it faces things no engine oil ever had to consider. The fluid may be in direct contact with electrical windings and insulation, so it must not conduct electricity and must not attack the materials it touches. It is increasingly used to carry heat away from the motor, as well as lubricate the reduction gearing. Motor speeds are far higher than engine speeds, so the gears see conditions that push hard into the elasto-hydrodynamic regime, and there is a failure mode that barely existed before. Stray electrical currents passing through bearings and eroding the raceways from the inside, which is a lubrication problem and an electrical problem at once. Alongside all of this, the way lubricant is managed has changed. For most of this history, oil was replaced on a schedule. Increasingly, it is monitored, sampled and analyzed for wear metals, for contamination, for remaining additive capacity, for oxidation. Wear metals in an oil sample identify which component is deteriorating and roughly how fast, which means a failure can be caught while it is still a maintenance decision rather than a breakdown. The lantern by the trackside has become a laboratory report. The question it answers is exactly the same one. Everything we have followed tonight comes back to one physical fact, and it is a fact about geometry rather than about materials. Two surfaces that appear smooth are not smooth. They touch at a scattering of high points, and at those points the pressure is high enough to weld them together and tear them apart again. That is the whole problem. Everything else, the tallow, the whale oil, the vacuum still, the soap network, the zinc compound, the ester built molecule by molecule, is an answer to it. And the answer, in the end, was never a substance. The answer was a discovery about how load can be carried. When Beauchamp Tower drove a wooden plug into the top of a bronze bearing, and the bearing pushed it back out, he was watching something that nobody had put into words, that a liquid, dragged into a narrowing space by a moving surface, will generate enough pressure to hold up a railway carriage. The metal is not carrying the weight, the oil is. Once you know that, the whole enterprise reorganizes itself. You are no longer trying to find a slippery material. You are trying to build and maintain a film, and every question that follows is about the film. How thick is it? Will it survive the temperature? Will it exist at startup? What happens where it cannot form? What protects the surface in the fractions of a second before it appears? 4,000 years of work, and the last century and a half of it spent understanding something that had been working, unexplained, the entire time. There is a particular kind of respect owed to this subject, and it has to do with how it fails. A lubricant that is doing its job produces nothing you can observe. There is no output, no motion, no measurement. There is only the absence of damage, accumulating quietly over years. The reward for a lifetime of correct lubrication is that nothing ever happened, which is why the knowledge tends to live in people rather than in books. In the man who could tell a bearing was going by the sound it made through the floor. In the machinist who knew which way to lay a film of oil on a way surface. In whoever it was, 38 centuries ago, who knew how much water to pour in front of a sledge, not too little, not too much. If any of this brought back a workshop, a smell, a machine you once kept running, you can leave it below when morning comes. Now, we have controlled friction. We have learned to hold two surfaces apart under load, at speed, in heat, for years at a time. But controlling friction does not by itself do any work. A shaft turning freely in a well-oiled bearing is only a shaft turning. To be useful, that rotation has to go somewhere. It has to be carried to another shaft, and along the way, it very often has to be changed, made slower and stronger, or faster and lighter, or reversed, or timed to something else with absolute precision. The way that is done is with teeth. And the strange thing about a pair of gear teeth, as we found tonight, is that they are the hardest place in the whole machine to keep a film of oil. A contact so concentrated that for decades the mathematics insisted it could not be lubricated at all. Yet gears predate almost everything else we have discussed. They were being cut in bronze when the theory that explains them was 2,000 years away. How engineers learned to shape a tooth so that it rolls rather than scrapes, how they learned to cut thousands of them identically, and how a mechanism from the ancient world became the most precise mass-produced object in industry, that is our next journey. And that is where we'll leave the machine tonight. Until our next journey, sleep well.